great pleasure to welcome Dr. Steve Schwartz as today's speaker. He's a senior scientist in the Environmental and Climate Division of Brookhaven National Lab, which is only 30 miles from here, the Department of Energy Lab, further east from here in Long Island. So Dr. Schwartz did his undergraduate degree from Harvard College. Then for his PhD, he went to University of California at Berkeley, and where he specialized as being a physical chemist, and his thesis was about chemical kinetics. And then for his postdoctoral work, he went to the University of Cambridge in England as a Fulbright scholar. So as you can see from the picture, he has the marks of an exceptional scientist. So afterwards, he spent a few years here in Stony Brook in the chemistry department, and then joined Brookhaven Lab, where he has done important work, as far as I know, in at least 3 different fields. First, back in the 1980s, the question of acid rain was the news, and so he did basic, very fundamental work on the conversion of gases like nitrogen oxide and sulfur dioxide into sulfates and nitrates. And his work is always process-oriented. He examines basic processes and systems. And if I remember correctly, his work had an impact on what was then finally legislated in the Clean Air Act amendments of 1990, after which the amount of sulfate and nitrate has decreased substantially, on the East Coast. After that, for many years, he worked on the chemistry and physics of atmospheric aerosols. And then in the last several years, he's focusing on some basic or really important problems in climate change, which other people don't pay attention to that much anymore. And today's topic is part of that. So Dr. Schwartz was the chief scientist for the Department of Energy Atmospheric Science Program for 5 years, and he played a key role in the development and implementation of the atmospheric radiation measurement program called ARM, on which many people have worked here in SoMAS also, ITPOS. And his, of course, work has been recognized by many honors, and so I would mention two. He is a fellow of the American Geophysical Union, and he is also a fellow of the American Association for the Advancement of Science. So let us welcome Dr. Steve Schwartz.
Okay. Good morning. Good morning, afternoon. Thank you, Sultan, for the very generous introduction, and thank you also for the opportunity to talk a bit about this work, which is brand new, and I'll try to explain as we go along how I got into this business, and try to give you as well a sense of why I think this is very important work, and a little bit of how it differs from previous work and why that might be important. Just sort of the vocabulary. CO2, carbon dioxide, anthropogenic, introduced by human beings. Anthropos, for those who study Greek, man, generically, our species. And how long does it stay in the atmosphere? Anthropogenic CO2. So why are we concerned about CO2? Why do we care about CO2? Why does it matter? It has a lot of implications on climate, as I think you all know. Why CO2? Energy. Brookhaven National Laboratory is a Department of Energy National Laboratory. We are concerned with energy. We all should be concerned with energy. To put things in context, standard adult diet for people who are not doing strenuous exercise is 2,000 calories, or actually kilocalories per day, which is almost exactly 100 watts. So think of yourself as a 100-watt light bulb burning 24/7. For an auditorium like this one, the engineers, the HVAC engineers, will figure how many people are going to be sitting in the room, and they're each putting out 100 watts, and so that's the amount of air conditioning we've got to supply to keep the room at the temperature that we want. So think of yourself as a 100-watt light bulb. The average per capita energy use, primary energy, of United States residents per capita is 10 kilowatts, 10 to the fourth watts, 100 times 100 watts. So think of your energy use as 100 of yourselves. You've got 99 others who are working with you to do what you have to do, all our energy use. Heating, lighting, transportation, get yourself from here to there, manufactured goods, agriculture, all of that uses energy, and so that in the aggregate, that's 10 kilowatts. Or 100-watt light bulbs burning 24/7, the equivalent of 100 of us. So each of these phantom people is exhaling carbon dioxide. We eat food, we exhale the carbon that's in our food, we burn it, we oxidize it in our muscle cells, really. And we exhale the carbon dioxide. So there's 99 others of us, the phantom people, that are exhaling all this carbon dioxide. And in some sense you know this, but I thought there's interesting factoids about sort of the magnitude of this, and that's why I like to start this talk this way. As a consequence of that, and we all know carbon dioxide measured in mixing ratio in the atmosphere, parts per million, 300 up to 400, time period 1960 up to the present, a measurement data set, and I'm a measurement kind of a guy, at Mauna Loa, Hawaii, initiated by one man, Charles David Keeling. And he had the hypothesis, the back-of-the-envelope calculation. Look, how much carbon is being burnt collectively by the people of the world, and it's going into the atmosphere, and atmospheric CO2 should be increasing, and prior to this work, there were some indications of that. And so he said, I'm going to build myself an instrument that's going to make these measurements, do it in real time, instrumental measurements, no wet chemistry, and get myself some measurements. I'm going to make a machine that's going to have 10 times the precision that I need to measure this increase, because I want it to be really good, and standards and accuracy. And so and what a wonderful data set. And this was really his career. He did much more than the measurements. He did a lot on the interpretation side. And these are monthly mean measurements of CO2 at Mauna Loa. Why Mauna Loa? It's at the top of a mountain. It's in the free troposphere. It's isolated from local sources. They exclude any upslope flow that there might be from the local sources in Big Island. Monthly means of these things, and set out starting making these measurements in 1958. And if you look at this thing, there's hardly a gap. There was 1 month when something was down, but basically there's hardly a gap in this record. And demonstrated to nobody's question, and that the CO2 is increasing over this period of time from when he started at something like 320, and it's up now to something like 410 parts per million, and it's climbing. And now imagine yourself, you're Dave Keeling, you're out there, and you make this measurement, and I got my first month's worth of data, and now I'm going to get the next month's worth of data, and get the next, and it goes down. And what's going on here? He's dejected. What's wrong with my machine? What's wrong with my hypothesis? Okay, but he keeps up the measurements, and it goes down to a minimum, and then it goes up. And the next year it goes a little higher, and it goes down, and it goes up. And then he realized what he's measuring, in addition to this increase that was what he set out to measure, is also something about the physiology of the biosphere. that in the northern hemisphere, where Mauna Loa is located in the tropics, 20 north or something like that, the vegetation comes out in the springtime. It draws down the carbon dioxide during the course of the summer. Comes fall, the leaves fall. They molder, they decay. The CO2 goes into the atmosphere, it goes up again. So not only is he measuring the increase that he set out to measure, but he's also measuring something about the physiology of the terrestrial biosphere. And that's also very important, and a very important part of the story that I'm going to be telling. So that's over this, what we call the instrumental record. We can, CO2 is increased. This extends that record back into time, back to 1750, and this is sort of what we call the onset of the Anthropocene, the era of the Earth's geology in which human activity has markedly affected the climate system. And these are now measurements from Antarctica, measurements from Cape Grim in the southern hemisphere, measurements, global averages. Now other people have taken up this trade, and a lot of measurement stations to get a reasonable global average. Here's the Mauna Loa record superimposed on that. They all fit nicely. Antarctica ice cores. Ice cores are our history. You take an ice core, you date it as a function of depth, and then you can measure the amount of CO2 in that, and you get the CO2 record going back in time, and that's where this comes back. Nobody's out at Mauna Loa measuring it back in 1750, but we've got the ice core's record on that. We can extend that. So this is what we just saw. Here's the Mauna Loa record. So the time scale of this is changing. Here's going back 10,000 years. Human civilization, basically. Adam and Eve were in the Garden of Eden right around here, tasting of the fruit of knowledge. But really the consequences of that fruit of knowledge, and God told them to be fruitful and multiply, and between the two of them, look at this, this huge step function in the CO2 on this kind of a time scale. It looks like a step function spread out over time, which we're seeing. But a consequence of what? Consequence of more people, and people discovering that there's energy to be had from burning things like fossil fuels. Dig some coal out of the ground, and you can light it on fire and get heat out of it, and you can then do work out of that and steam engine and take it from there. Titusville, Pennsylvania, somebody drills a hole and gets oil out, and okay, so you know all that story. So here's 10,000 years. Here's the last glacial cycle. So last ice age, 20,000 years ago. The last interglacial, kind of like what we have now. But look at this, way up here, like what we had in the pre-industrial times, not like what we have now. And then extending this back the whole 800,000 years, which is the extent of the depth of the glaciers in Antarctica, and you can see the multiple glacial interglacial cycles. And you can see here's our pre-industrial, which is at 278 parts per million, and here's where we are now, and totally unprecedented. And that's, in some sense, so what? What do we care? But we care a lot because of the radiative influence of carbon dioxide on the Earth's energy budget, which I'm not going to get into, but that's what's really motivating much of our concern these days. Okay, where's it all coming from? We kind of know that. I kind of hinted at it. It's us collectively. What's shown here on this chart is emissions. Units here, petagrams, 10 to the 15th grams, or 10 to the 12th kilograms. Or gigatons, some people prefer, per year, going up to the present value of 10 or 11 or so. Color-coded, the red is fossil fuel combustion. The green is what we call land use change. That's the terminology that's used in the trade of deforestation or net deforestation, deforestation minus afforestation. If you had agricultural lands that were initially cleared but then subsequently forest growing on it, you have to take that into account. So where these numbers come from? They come from inventories. A lot of hard work goes into getting these numbers. Uncertainties on them, especially on the land use change numbers there. The the sum in the blue with the uncertainties carried over. Interestingly, these two curves don't cross until something like 1950. So the subsequent to 1950 is when we're really starting to pump the CO2 into the atmosphere from fossil fuel combustion. So that's emissions. This is now cumulative emissions, so the integrals of those previous curves. So this is now petagrams, integral petagrams per year. The year is petagrams. Okay, so here's the total from the land use change in the green, from the fossil fuel in the red. When did these cross? They crossed something like 1980 because of the persistence of the CO2 in the atmosphere. And then the sum of those, which is going up to something like 650 petagrams of carbon that we collectively have put into the atmosphere through combustion of fossil fuels and from land clearing activities. And now I put on this other scale CO2 in parts per million with the zero scale at the pre-industrial 278, and then all these circles are the measurements that we've just seen previously. And then here's the emissions on the scale that if I took the total amount of CO2 that I've emitted into the atmosphere, divide by the volume of atmosphere, how many ppms that would have been if it had all stayed in the atmosphere. That's this number, and it would have been up to something like 560, 570 parts per million. But hey, we're only at 410. So why? Why are we only at 410? Where's the rest of this gone? And that's in some sense the subject of the talk. What's responsible for this? And it's commonly referred to as nature's subsidy of our carbon dioxide emissions. It's not staying all in the atmosphere. It's going someplace, and then where's it going and how fast? And that's really the question here. So I've got this title here, Motivation for this Study. There's really two motivations. One, we want to know the answer to this collectively because it's going to, it's essential. Knowledge of this is for planning purposes. If the CO2 lasts longer in the atmosphere, that's bad news because the more we put in, the longer it's going to stay and the more it's going to accumulate. If it lasts a shorter time in the atmosphere, that's in some sense good news because it's not going to stay so long. And that number needs to be known. If you're in an energy planning business, which the Department of Energy is nominally in, that you have to say, oh, how much energy, how much CO2 can we emit, and the implications on energy in order to achieve this or that desired target. So that's in some sense, the motivation for the study. But then there's my motivation. How did I get into this? And as Sultan mentioned in his introduction, I've been thinking about aerosols. I've been thinking about climate, but I wasn't thinking much about CO2. But I did a paper published last year, JGR, which I call the cold turkey experiment, which for those who are not native English speakers, cold turkey means if you have an addiction smoking alcohol and you quit abruptly, that's called going cold turkey. Or more formally, the abrupt cessation of emissions. What would happen to global temperature if we abruptly ceased the emissions and we were in some sense committed with either present atmospheric composition or the substances that are influencing climate start decreasing according to their natural lifetimes? What would be the consequences of that on global temperature? And so that's how I got into this. And I kind of assumed CO2 is long-lived in the atmosphere and not to worry about that. I'm really focusing in that experiment on atmospheric aerosols. So I think it's a very important figure. I think it's a very important paper. It hasn't gotten a lot of attention. But atmospheric aerosols, just a brief statement about them. Particles in the atmosphere that scatter light. They modify the properties of clouds. They thereby influence climate, Earth's radiation budget, and therefore climate. And they're short-lived in the atmosphere, about a week. We know that on a whole bunch of grounds. So if we were to stop emitting largely from fossil fuel combustion, aerosols and aerosol precursor gases abruptly, aerosols are going to disappear in a week's time. Well, in the terminology of the trade, aerosols exert a negative forcing on climate change. They exert a cooling influence, offsetting some fraction of the warming influence of the increases in CO2. But it would go away in a week. And then what's going to happen? And so this paper examined the implications of uncertainties in aerosol forcing, the radiative influences of aerosols, and of climate sensitivity, how much climate change, how much temperature will change for a given perturbation in the radiation budget, as a consequence of ceasing the emissions, the abrupt cessation of emissions of anthropogenic aerosols. And within the current uncertainties, if the climate sensitivity is low, and if the magnitude of aerosol forcing is also low, and those are coupled because of the constraint from observed change in global temperature, then if you abruptly cease and the temperature is going to increase by something like 0.1 Kelvin, 0.1 degrees C, as a consequence of that. If, on the other hand, the aerosol forcing is high and the climate sensitivity is high, you're up to something like 1.3 degrees Kelvin Celsius as a consequence of the cessation of the emissions of aerosol and aerosol precursors. And that's why I think this is very important, because these are, I didn't make up these uncertainties. These are the uncertainties that come to us from the analysis that's in the IPCC fifth assessment report. And so I just use those numbers together with observations to come up with this. And one point, here's the Paris, this is on the scale of relative to pre-industrial temperature. We've already increased 1.1. Here's the Paris target of 2. We would bust through that if we're up here, and we don't know. And so I think this is real important, but as I say, it hasn't gotten a lot of traction, but, and we can get into the psychological reasons for that. But as I say, very, very important. Okay, well, back to CO2. If we put in decay of CO2 on top of that, on the century time scale, here's 100 years, no decay of CO2, or various estimates of the lifetime of atmospheric CO2, it modulates this result somewhat. The primary influence is the aerosol influence, the secondary influence is the CO2. So how did I learn that? I had to look at the CO2. So here's just the CO2 itself. If we were to cease the emissions of CO2, and if the lifetime of the CO2 is infinite, which is the solid line, or 500 years, or 200 years, or 70 years, then here's what the global temperature is going to be, depending, again, on the assumption of the climate sensitivity. So there are a lot of uncertainties here, but the big one that caught my attention in this part of the study was the CO2 lifetime. And so that's what's shown on this chart. So this chart is taken from that paper. I've extended it out to 100 years. It's a semi-log scale. So an exponential decay with the lifetime of, say, 200 years would be this dashed line. Here's 500 years, here's 100 years, here's 70 years. And here is a whole bunch of models. And these are reasonably current models. It's an ensemble of convenience in the sense that these people didn't all do the same experiment. Some people started, well, let's assume it goes up to 550 parts per million, and then we abruptly cease the emissions of CO2. And somebody else says, no, let's assume it goes up to 2,000 parts per million, and we stop the emissions of CO2. So I normalized them all. I said 100% of the time you cease the emissions, and I plotted them all on a semi-log scale. There's a lot of work getting these data and plotting them up. And you see the spread, and the spread is tremendous. And the first thing, when you plot something like this, and one of my mantras is if you're going to compare data, you got to plot them on the same piece of paper. And so we put them on the same piece of paper. And you look at this and you say, these can't all be right. And so that's what kind of intrigued me. This thick dashed line is the multi-model mean from a model intercomparison study that is used as the basis of what's called global warming potential of carbon dioxide, how long it lasts in the atmosphere, integrated by over time with the radiative forcing thrown in. And so that's what's used in current assessments. But is it right? Well, depends on the spread of those models was huge, and that's the multi-model mean. So that's really what got me into this. And I'm going to cut to the quick. Here's my result. So here's what I find from the model that I've developed. And I'm going to try to, in the time that remains, show you how I got this result and why I think you should believe it, and why I think the referees of the paper should believe it, and a little bit about why it's important. So I have to talk somewhat about lifetime. Life, we know what a human life is. What's the average lifetime of people? Well, you take the number of people that die in a given year, and you take the number of people that are in the population, you divide them one into other. That's one way to get a lifetime. So we have a sense of a lifetime, but we need a quantitative definition. This is from a paper by David Archer and a whole bunch of others who did this kind of study, and they came up with, I'm sure collectively they debated this a lot, the amount of time it takes until the CO2 concentration in the air recovers substantially towards its original concentration in the absence of emissions. That's important. They didn't put that in there. Okay, so we're going to take that as a kind of a qualitative definition. The time required in the absence of anthropogenic emissions until the CO2 concentration air recovers substantially towards its original concentration. Well, to answer that question, you need a model, because we could do the experiment. We could turn off all anthropogenic CO2 emissions and wait and make the measurements, but we're not gonna. So it requires a model. There's also getting quantitative in terms of our definitions. There's a quantity that's called the turnover time. And the turnover time is the ratio of the stock in a given compartment, let's say the atmosphere, divided by the sum of all the fluxes that are going out of that compartment. So it requires a budget, not a model. You need to specify which stock, that's the atmosphere, or maybe not, and which fluxes, because there's if you think of the terrestrial biosphere, for example, you've got the drawdown and the return, and how are you going to count all those? I'm introducing here what I'm calling the delta method. If I take the stock, I know the emissions, Q. So I know all the anthropogenic emissions. How do I know this? By inventories. I subtract from that the annual increase in the stock. And then I take that difference and I divide that into the magnitude of the stock. So let me run this through in a way you can assess. You're employed. You get a salary. You put the salary, your paycheck in your bank account. And you and your spouse are saying, well, gee, what happens if I lose my job? How long will the money last? Well, we could look at all the checks that we've written and which ones we're going to count. Do we count the ones that go to our brokerage account? No, you can't count those, because those are just moving money from one place to another. That doesn't really count. Well, alternatively, you can say, well, look, let's figure out how much money we got, total aggregate money we got. And look, last year we got a paycheck, so that went up, but the amount that our money went up wasn't equal to the amount of our paycheck, because we spent some money. So we're going to subtract that. So here's the money we got in our aggregate, and here's the paychecks we got for the year, and then we're going to subtract from that the amount by which our stock went up, our total worth went up, and then that's basically how much we spent. We take how much we spent, we divide that into the stock, and that's how many years our money would last if we lose our job. So that's a calculus. So think of the delta method or the bank account method. Then there's another quantity called the adjustment time. And the adjustment time is like on the semi-log plot. If you take the stock and you divide it by the negative of the slope, the rate of change of that, and divide the local instantaneous rate of change into that stock that you've got in the absence of emissions, then you get what's called the adjustment time. And so these are different measures, but if we understand the system, they ought to agree reasonably closely one with another. And so that's kind of a check on understanding. So this one requires a numerical model to get This one just requires a budget. So that's the direction we're going to go in, and we're going to start with this observationally based global CO2 budget and the turnover time. And we're going to get that really from observations. So this is a very complicated chart. It's got a lot of numbers on it. It is, in some way, repeated over and over again in a bunch of assessments, and the numbers change slightly. The picture stays more or less the same. Picture's gotten glitzier in the later versions of the IPCC assessment reports. This picture is from the figure 7.3 of AR4, the fourth assessment report, but it's got a lot of numbers on it. And when you look at a picture like this, you have to say to yourself, where do these numbers come from? And every one of these numbers has to come from someplace, and that's what I'm going to try to lead you through in the next series of slides. Some color coding. Black is pre-industrial. Red is the anthropogenic perturbation. Blue is the annual growth. So that's the increase. The blue is the increase in our bank account. The sum of the red and the black is how much money we got in our bank account, so that's the color coding. The upright type, non-italic, is the stock in a given compartment. The italic, the slant type, is the flux, and that's probably all you need to know in order, in terms of the introduction to this figure. As I said, there are a lot of quantities on it, but before I leave this one, simplifying. Here's the anthropogenic emissions from fossil fuel, about 10. Here's anthropogenic emissions from deforestation, land use change, about another 1.4 on that. And so we're up to 11 or something like that. Here's the flux into the terrestrial biosphere, 120. So 120 going down, this is what the plants are growing down from the atmosphere. And of that, 119.4 going back. So there's a lot of traffic on this compared to the magnitude of that flux. And that's important to keep in mind when we go through this analysis. Okay, moving into the simplification of this, I think I've said all I want to say about the template itself. So here's already greatly simplified. It's just the black. It's just the pre-industrial. This is back to Adam and Eve. To call attention now to some numbers. The system is in steady state. As a chemist, I call attention that you can learn a lot from and it imposes a lot of requirements on your analysis, which is helpful. The amount in the atmosphere, the stock in the atmosphere, pre-industrial atmosphere, we know that. That's from those glacial ice cores, and we know exactly what that was. We can take ppms and we convert that into petagrams, and it's 590, roughly 600. Okay, measured. How much is in the ocean mixed layer? Oh, I should have explained the compartments. My compartments are the atmosphere, the mixed layer ocean, the deep ocean, and the terrestrial biosphere. 4 compartments, and then I've got exchange fluxes between the several compartments. The mixed layer ocean is taken as 100 meters. It doesn't matter exactly what number you take, but you need a number in order to make the calculation of how much is in this stock. It's about 900, written to many more significant figures than is justified. All these numbers are shown to more significant figures than are justified. How do we know that? Basically, calculation. We know that this system this one's actually going to be in near chemical equilibrium in the pre-industrial steady state. There's not a lot of perturbation on the system. We can make that calculation and calculate this number. It's actually slightly out of equilibrium. We've got 70.6 going up, 70 coming down. We'll come to that in a minute. So that one's pretty well known. Is it a constant spatially? No. It depends on temperature. It depends on salinity. It depends on this and that and the other. So this is a kind of a gross number, but nonetheless useful. This number, the gross primary productivity, I say measured, it's more or less measured. People go out and make their living trying to measure how much plants are growing down by things like eddy correlation measurements, and then and you can measure how much is going down. That's the gross primary productivity. It's a tough measurement because the plants are respiring. They're respiring. You can measure it at night because you don't have any photosynthesis going on at night. It's tough to measure the respiration rate during the day. Plants are using, why are plants fixing carbon dioxide with the solar energy? They're doing it for energy. The plants need this energy to do all the chemistry that's downhill from the sugars that they initially produce. They produce these sugars in the photosynthesis, and then they got to use those sugars for building structural materials, building the roots, you name it, putting out the leaves. So all of that is respiration, and it's just about the opposite. This is a tough measurement to make. And I got the 120 down here, and Christian Baer's paper in Science a few years ago, 123 plus or minus 8, and then somebody else comes up with a number, no, it's 160. So we don't know that number all that well, but it's more or less measured. The stock in the terrestrial biosphere, that's also more or less measured by inventories. You go to every piece of real estate in the world, and you count the amount of carbon that's in the biomass above the soil, and then you say, well, I'll take a soil horizon of 1 meter. Oh, you're going to use 1 meter, I'll use 1 meter. Okay, so they settle on 1 meter, and they integrate all that up, and that's the 2,800 petagrams of stock there. This number turns out to have some importance, and not all that well known. So that's where those numbers are coming from. These two things are nearly equal, as I've mentioned. What about this one? I'm calling this a universal deposition velocity. Gases exchange with surface water. All gases exchange with surface water. If they're not all that soluble, carbon dioxide not all that soluble, the rate of exchange is controlled by the rate at which the surface layer of the ocean gets, micro layer of the ocean gets mixed into the deeper part of the mixed layer of the ocean. And that's the same for all gases, and that's why I'm calling this universal, but putting in the atmosphere depends on the Henry's law of solubility of the gas, but it's still universal. We know those numbers. Okay. This is exchange between the mixed layer ocean and the deep ocean that also assumes a certain amount of importance. It's also universal. Any tracer will work for that. And the way I came up with the number that I came up with was by using heat transfer, because we know a lot about that from measurements of heat content of oceans as a function of time, and then you get, it's increasing, so you're getting a heat accumulation rate into the deep ocean. You can get a piston velocity exchanging those two compartments from that kind of analysis. Uncertain is something like 30% or 50% on those two numbers. So the 70 and 70.6, they're uncertain to 30%, but we've gotten to more significant figures because we want to show this 0.6 difference. So where's this 0.6, which assumes a certain amount of importance in this discussion? You have the drawdown, here's the 0.6 difference, and then some of that goes in rivers to the mixed layer ocean, and so that's why the mixed layer ocean is a little more supersaturated than equilibrium, and that's why you have this exchange here. It's a steady state, not quite an equilibrium. These two are nearly equal, so it's near equilibrium. We can calculate this flux very well under the assumption of this one because of detailed balance considerations in chemical kinetics, so we know how to do that. There's also a disequilibrium between the concentration of carbon in the deep ocean and that in the mixed layer ocean because biology, again, phytoplankton are fixing carbon. They make particles. These particles sink. They dissolve into the deep ocean. They get oxidized into CO2, and you've got a do-nothing cycle here of a fair amount of magnitude, about 6 petagrams per year on that. But it's a do-nothing cycle. But it does impose a disequilibrium between these two compartments. We can get time constant out of the system already. So we know the amount of stock in the deep ocean, the volume times the concentration, and we divide by a lifetime, a flux of 55 coming up out of that, and we get something like 600 years for the lifetime of the carbon in the deep ocean. Is that a real exact number? No. You've got pockets of deep ocean that don't exchange. You've got pockets that exchange more deeply. It's arbitrary by this 100 meters. And we get a lifetime in the atmosphere. We say, look, we've got something like 600 in the atmosphere. We got 120 going down here, 70 going down here, 200, 200, and 600. We're getting something like 3 years. So that's the lifetime in the atmosphere of carbon dioxide in the atmosphere. What lifetime? It's the lifetime of an individual molecule. If you put in carbon-14, for example, that's the rate at which the carbon, because you don't have a backflux of carbon-14. So that's the rate at which the mean lifetime of an individual molecule, but not relevant to our discussion. Now we want to come back to the anthropogenic perturbation, so I'm going to go through these numbers in exactly the same kind of way. We measure this, we know this one's to a gnat's eyelash, we can calculate this one to a gnat's eyelash, so we know those two numbers. We can use exactly the same deposition velocity for this flux down, the detailed balance argument for that flux up. The universal piston velocity takes us here, so we know all of that. Land use changes by inventory, emissions by inventory, so we got those numbers. We know everything else. We know how much the atmosphere is increasing. The only thing we don't know, my pointer is going, a battery on my pointer is going, so I'm going to move over here. The only thing we don't know is the flux into the terrestrial biosphere, but by conservation of matter, we know that because we know everything else, and so therefore we get the flux into the terrestrial biosphere, and that's a big one. So that's just 4 on these units. I'll manage with this. Okay. Now we get another lifetime out of it. We're getting the lifetime out of that, which is the anthropogenic perturbation in the mixed layer ocean, that's the 32, divided by this flux out of about 30, that's about a year. So we're already getting some important information. That's short, 1 year, that's a short time. That means that these two compartments are going to be usefully considered in equilibrium one with another, and that's going to simplify our lives. And we're going to get the one we really want, which is this turnover time, which is this 260 plus 32, that's 300-ish, divided by 10-ish, minus 10 minus this atmospheric growth of 5. So it's 300 divided by 5, that's your 55, 60 years. That's the turnover time of carbon dioxide in the combined compartments of the atmosphere and the mixed layer ocean, treated as a single compartment, and we know we can treat them as a single compartment because the equilibration time between those has a short lifetime. So that's, in some sense, done. I've got this 54 years, I'm done, I can quit, I've got uncertainties on it from the measurements, but I'm done. But that's not going to work. I need a model. So I'm going to take all of these quantities that I've been working on and put them into a model. So I've changed the differential equations, 4 differential equations. I've got 4, I'm losing my pointer, 4 different compartments: stock, in the atmosphere, mixed layer, deep ocean, terrestrial biosphere. Exchange coefficients, which are determined from observations, both directions, and sources. And that's my set of differential equations. So I've got that. I can now get transfer coefficients from observations. So every one of these fluxes it corresponds to a transfer coefficient. My K, my subscripts A for atmosphere, M for mixed layer. K is the transfer coefficient between the two. It's the flux in the pre-industrial atmosphere. We know that. The stock in the pre-industrial atmosphere. We know that. We've got it. It's a geophysical property. It's a property of Earth's climate system. I got no latitude on that. I've got uncertainty on it, but I got no latitude on it. KMA, I know that because of acid-base chemistry. That's the reverse coefficient. My exchange between the mixed layer and the deep ocean, again, it's a geophysical property. It's from the observed heat uptake rate. It's the same for everything. I got no latitude on that. I got uncertainty, but no latitude. It's not an adjustable parameter. My K from the atmosphere to the terrestrial biosphere, that's a CO2 specific as opposed to universal. And how do I get it? I'm getting that essentially by the bank account method. I know how much I'm putting in. I know the changes in stocks of the other compartments. I divide, subtract those, I divide, and I've got a K for exchange coefficient from the atmosphere to the terrestrial biosphere. And I can do the reverse direction because under the pre-industrial conditions, there has to be a steady state, and the steady state if it were equilibrium, would be this term, and there's a slight perturbation from that 0.6. So I'm done. I've got all those numbers. I want to introduce a quantity that I'm referring to as obdurate carbon. And obdurate I've chosen because nobody else used that word to describe this stock of carbon. People are using the term recalcitrant carbon, refractory carbon. I didn't want to use that and confuse the definition, so I've got the obdurate carbon. This is the pre-industrial steady state, and it defines the flux of this obdurate carbon. The flux from pre-industrial, from the atmosphere to the terrestrial biosphere, is this KAT, which we've just determined, times the stock in the atmosphere in the pre-industrial. It's also equal in the opposite direction. We can equate these things. We can get a number for the KAT and so forth. We get this flux of what I'm calling obdurate carbon of 8.79 petagrams per year, much less than the gross primary productivity. And this is the rate of uptake and loss of long-lived carbon in the terrestrial biosphere. So I'm putting that on the chart, and that's shown over here. This is my 8.7 that's showing up on this particular chart. I can get a lifetime of this obdurate carbon by the stock upon the flux. And I do that, and I'm getting a lifetime of something like 300 years. So is that a reasonable number? I think so. Think, where's the carbon in the terrestrial biosphere? It's in trunks, it's in branches, it's in soil carbon, all of which are long-lived. The leafy stuff that you see is very little carbon in that. That turns over quickly, but the trunks and the soil, that's where the carbon is in there for the long time. So then most of it. I have a paper submitted, got the reviews back. One of the reviews says, "Oh no. You can't. You must take into account this lifetime of carbon in the terrestrial biosphere, and here's the citation, and it's 23 years. No, it's not 23 years. 23 years is sort of it's based on that gross primary productivity, and that's just not the right flux to divide into that to get a lifetime. Okay, one other thing. I've assumed that this KAT from the atmosphere to the terrestrial biosphere is constant over time. I can plot that from observation. So all of these are observations of what that quantity would be. And then here's the constant number that I came up with, which is represented by that blue slope. To run the model, I need emissions. We've seen this. I'm going to compare with observations and sort of moment of truth. Put all these numbers in the model and push the execute button. Whoa, there it is. So I was very pleased with this, okay, now I've got a model. It works. It reproduces things in the past tense just fine. I can use this with some confidence. I can compare this model again to the observations, which I just showed you, and the model's doing just fine on that. I can say, what happens if I turn off the emissions? And so I'm turning off the emissions in year 2017, and the CO2 goes down. Okay, now I've got what I want. I can fit that to an exponential decay curve. I get a lifetime of about 60 years. I could do this again, turning off emissions in 1967, 50 years ago, in 1917, again, the same kind of lifetime, slightly different, shorter. I can use this model to look under the hood and see where the various stocks are, where the carbon is going into the various stocks. The uptake by the terrestrial biosphere and net loss of net terrestrial biosphere because of deforestation, giving us this green curve. The deep ocean, the atmosphere is going down. I can look at the fluxes, which is shown here. Important part of this figure is that these fluxes, for example, into the deep ocean and the terrestrial biosphere, don't decrease when I turn off the emissions. The fluxes don't know about the emissions. They know about the stocks. Why is this green one jumping? Because we've turned off the source from the deforestation. I can look at that equilibrium between the mixed layer and the deep ocean. I can now compare with observations and with other models. Here's my model, anthropogenic ocean uptake as a function of time. Here's a representation, a measurement based of that. See if my pointer's working. Nope. measurement-based estimate of that based on surveys of dissolved CO2 in the 1990s and again in the 2000s, and look at the increase and divide by that. So that's that measurement. There's a lot of confidence can be placed in that. Another set of measurement-based calculation of that flux based on radiocarbon. Another whole bunch of people who've been making these measurements by integrating over the surface ocean. Some models that are in the Global Carbon Project. Some more models that are in the CMIP5 intercomparison. Are all these models right? No. Is my model right? Not necessarily, but it's in the ballpark. Do I take some confidence in my model from this? Maybe a little. And so the manuscript has a lot of those comparisons. I can now compare the lifetime of carbon dioxide I get by multiple means. This is the turnover time that I got from observations. I can get the turnover time from the model as a function of time. I can get the turnover time of, the blue one is the turnover time of the mixed atmosphere, mixed layer, the combined atmosphere mixed layer compartment. Do it just for the atmosphere and you get a big jump right here because you're no longer draining the atmosphere into the mixed layer for the mixed layer to try to keep up with the atmosphere. I can get an adjustment time for the atmosphere and mixed layer. Adjustment time for the atmosphere only. Analytical from the eigenvalues of the differential equations. Fits to the decay curves. Do it at a whole bunch of different times. The point that I'm trying to make is that no matter what I do, I'm getting numbers that are sort of in the maybe 45 to 60 year time scale, and they're all in concurrence with one another. So it gives me a lot of confidence in the claim that I'm making for that kind of a lifetime. Say a word about free parameters. You have a model, you can make adjustments in them. If you have parameters, there's a saying that goes back to really von Neumann. And the story is told in this biography of Fermi's. And Freeman Dyson comes in. He's got a model that fits some observations. And Fermi says, how many free parameters did you have? And Dyson says, only 4. And Fermi smiles. Why is he smiling? Because of the saying from von Neumann. With 4 parameters, I can fit an elephant. And with 5, I can make him wiggle his trunk. So how many free parameters do we have here? Really only 1. What's the amount of carbon stock in the terrestrial biosphere? So here's my base case. I can say that the transfer from the terrestrial biosphere back into the atmosphere is 0. That's this one. I can decrease that terrestrial biosphere stock by a factor of 3, or now a factor of 6. I get a nest of curves. They don't change much. They all have comparable lifetimes in sort of the 50 to 90 years. And this one, with the 90, is already markedly departing from observations. We can exclude that from the basis of observations. So, yes, we can make the elephant wiggle its trunk, but we can't make the elephant wiggle its trunk very much. And that's the thrust of this particular analysis. Kind of quickly, what if? We have a model, we can do what if. How would we stabilize CO2? If we cut emissions in half, which is the nature subsidy, we would stabilize CO2 and we'd know it next year. It would show up immediately. So that's what I consider very encouraging result. So, conclusions. Lifetime 50 to 60 years. Much shorter than most current estimates. We could stabilize by halving our emissions. This would all be good news. And this 4-compartment model, 3 observationally constrained parameters, I think it really reproduces the system and gives us a lot of confidence in this model with minimum adjustable parameters. So let me leave you with this final slide, which is putting my results on the same scale as all these other models. And with that, I kind of breathlessly thank you for your attention in the seminar.
Already come to a few questions. Yes, Marat?
Yeah, but just this is very profound. I used to always teach that that even if you stop emissions like for hundreds of years, it's going to stay.
I can't. I'm here.
No, I mean, I used to teach like that if we stop emissions today, like we still have all this, because it's everywhere, it's all textbooks everywhere. Like for hundreds of thousands of years it will stay in the atmosphere, but apparently it's not so. Completely, it's completely different number that we show here. And that's my question, what, we have this pattern period, 60 million years ago, 55 million years ago, when the amount of CO2 was factor of about 868 than today, I mean higher. So based on this kind of, if it's like half time was like, I don't know, if folding time like 100 years even, that would require tremendous, huge, unbelievable, and then based on this figure, amount of emissions of CO2, where it could come from. I don't understand.
Yeah.
Can you repeat that question?
Yeah. What Murat is asking, observing in the first instance, is he used to think that and taught that the CO2 lifetime is long, which I also thought and assumed. And here I'm coming up with a short number. But then he's posing a very good question, which is, okay, what about 60 million years ago when the CO2 was much higher than it is now? If the sink rate into whatever was serving as the sink at that time, to have such a high concentration requires either high emissions or a lower sink rate, which I think would be fair. And I think it is fair, but it's not fair. I think we can learn a lot from paleo, but the issue then would be, it's a steady state, and under a steady state, the emissions and the sources have to be equaling each other. It's a slowly varying steady state, but under those circumstances, they have to be equal and opposite. So whatever those sources and sink rates were, and I don't think we know them, we know the concentration, they're going to be equal and opposite to each other in order to maintain that steady state. So I don't know that we would learn a lot. The nice thing about the anthropogenic perturbation, if you have a system in chemical kinetics that's in steady state, you can't learn much about it. But if you perturb the steady state, Manfred Eigen Nobel Prize for T-jump experiments, then you can learn a lot about the kinetics. So I don't know what we can learn about these kinetics. I'm not saying dismiss the paleo, but it's a tougher problem.
So Steve, you had it. So Christopher, you had it.
Well, it's sort of it's a similar question to Murat in the sense that it's a question is why did the other people get such high numbers compared to your number?
Yeah, the question is, why are these other models getting such high numbers? I don't wholly know the answer to that. My model, I can easily look under the hood and see what all the fluxes are and what's happening and so forth. I don't think the models are going to be too wrong on the ocean uptake. So it has to be in the terrestrial biosphere. It has to be the treatment of the terrestrial biosphere. Why is the terrestrial biosphere in these carbon cycle models not drawing down as much CO2 as I'm inferring is being drawn down by the fact that I can calculate with confidence how much is going into the ocean, and I know how much the atmosphere is increasing, I know how much the emissions are, so I have confidence in how much, by difference, how much. Do I have a lot of confidence? No, because there's uncertainties, especially in the exchange coefficient piston velocity from mixed layer to deep ocean. I need to explore all of that. But the bottom line is, it's a trade-off. If I increase the one, I decrease the other, but the net is not going to change. So I have a lot of confidence in that 4 petagrams per year drawdown into the terrestrial biosphere, or the sum of those two into the terrestrial biosphere mixed layer, which is where I got my lifetime. So it's going to be interesting to sort this out as to why the carbon cycle models are getting such a spread amongst themselves and such a systematic difference from the number I'm getting based on observations.
Yes, Edward.
It's just surprising that you're getting your 4 milligram per year from differences between large numbers, and you're kind of suggesting that your uncertainty that is pretty small.
Yeah, they're actually not. What Evan's asking is I'm getting my 4 as differences of large numbers, and he's surprised that the uncertainties are as small as they are. They're not such large numbers. The total emissions are 10 or 11 petagrams per year. The uncertainty on that is something like a 1. From that 11, I'm subtracting a 5. I'm getting something like a 6 plus or minus 1. So that the stocks we know. So the 6 plus or minus 1, that's 15%. So it turns into the 50 plus or minus 10. So it's not an inconsistent uncertainty.
Last question is from Professor Nico. Yeah, go ahead.
Yes, zero emission, particularly worldwide, is a goal difficult to reach. More practically or more reasonable, probably 50% or 20%. With that amount still emission into the atmosphere, will that amount continue to affect your lifetime?
The question is sort of twofold. One is we may not achieve zero emissions. We won't immediately. Even 50% might be difficult to achieve. How is the lifetime going to respond in the future to these changes? The first order question is, what's the lifetime now? And I think I've got an answer to that. Second order question, what would that lifetime be in the future? And my model tells me that, and it does increase with time. Why does it increase with time? It increases with time because the back fluxes out of the deep ocean back into the mixed layer and into the atmosphere, the back flux from the terrestrial biosphere into the atmosphere become an increasingly large fraction relative to what's being drawn down when we've reduced the emissions. So that's the real reason the lifetime is increasing with time, is because this back flux is offsetting increasing amounts because of decreased emissions. If you maintain the emissions high, the lifetime is not going to change so much as if you did the abrupt cessation experiment. But the first order question is, what's the lifetime now? The second order question is, can we play some what-if games? Yes, our model allows us to do that. And I gave you one example of that. We could stabilize for some decades with cutting our emissions in half. But ultimately, the return fluxes are going to come back and bite us, and we have to reduce some more.
I think the last, do you have a question?
Oh, I have a question. Yeah. To what extent, so once you cut emissions, the 300 years that you're talking about for forests, will that affect also a reduction in forest fires if you have maybe a reduced temperature for CO2?
Yeah, the question is, okay, if we were to reduce emissions, would that bring about a reduction in forest fires and wildfires? I presume you're referring to. I don't want to speculate in that direction at all. My perception of the reason for the increase that we've had in wildfires is more from climatic changes in climatic conditions than it is from carbon stock.
So Dr. Schwartz will be available to speak to graduate students at 1:45 p.m. the lunch room.
What time of meeting?
So that is very good.
Okay.
So then.
Okay, we have lunch. Join us for lunch, and I'll be more than happy to meet the students at commencing at 1:45. Okay, thank you.